I'm going to continue on here in our 6-1 lectures. We're looking at defining our trig functions using right triangles. We got into introducing our special angles. There's 3 special acute angles that we mentioned. We're dealing with these triangles, and that is a 30, 45, and 60 degree angle. So going back, looking at our 45 degree angle, I want to look at finding the trig function values, and these are values that we want to know. We're going to spend time with them all semester. We're going to use them as reference as we move on to different angles from different triangles, different rotations, different approaches as we move through the semester. But in introducing the 45 degree angle, we can do that with a drawing of an isosceles right triangle. So an isosceles right triangle, of course, is a triangle with a 90 degree angle and 2 congruent sides, those being the 2 legs of that 90 degree angle. With that, we let the lengths of those sides be 1 unit. You can let them be whatever length you like, as long as they're the same. It's an isosceles right triangle. And we know from geometry of an isosceles triangle, if those 2 legs, those 2 sides are congruent, the angles opposite those 2 sides are congruent. So with this being a right triangle, we know the other 2 angles must sum to 90 degrees because all 3 total 180. And then they're congruent, they'd have to each be a measure of 45 degrees. So that's why we can use an isosceles right triangle to prove our trig function values. And we did that by finding, of course, then the hypotenuse, which would be the side opposite 90 degree angle, the missing side in our isosceles right triangle. So we did that with the Pythagorean theorem, which is the square of the hypotenuse equal the sum of the squares of the 2 legs. And that derived down to the square root of 2, an irrational number, which again is a non-ending decimal. Of course, we want to leave it as a root, right? So we want to leave the exact form. And we did that, and you can see our definitions reviewed here with sine, cosine, tangent, and their reciprocals. Cosecant, secant, cotangent. Sine, remember, definition is opposite over hypotenuse. So again, these trig function values are calculated by looking at the ratio of the lengths of the different sides of your right triangle. So sine is always opposite over hypotenuse. Of course, cosecant is reciprocal, so it's hypotenuse over opposite. Cosine is adjacent over hypotenuse, and its reciprocal function secant, and its hypotenuse over adjacent. Tangent's opposite over adjacent, it's the ratio of the 2 legs. And cotangent's reciprocal function will, of course, be adjacent over opposite. And you can see the values. Sine of 45 degrees, of course, square root of 2 over 2. After we rationalized the denominator, we wanted to get rid of that square root in the denominator, so we multiplied by the square root of 2. So we could create the square to get rid of it. So you can see the work there behind that. Just a summary of what we finished off with before we left in our last video. I want to show you how to derive the trig function values for 30 and 60 degrees. And if you want, we can take a look at it on our calculator. Of course, your calculator, it's not going to always give you the exact value. You want to be able to know these or find these values without a calculator involved. We want to know these. We want to have them memorized because we're going to keep using them, as I mentioned earlier, as references for other angle measurements as we look at evaluating different trig functions. In a right triangle, if we look at an equilateral triangle, we can form a couple of right triangles by dropping in the height, dropping in the perpendicular, right, on this. Let's look at it here together. So I'm going to go ahead and draw it in here. So if I ask for the height of this equilateral triangle. Now, a little review quick before we begin. We know in an equilateral triangle, of course, all 3 sides are going to be equal length. And all 3 angles, of course, are congruent, with the 3 sides being congruent. So with that said, in our equilateral triangle, our 3 angles will measure 60 degrees, right? Because each are congruent. All 3 must add to 180. 180 divided by 3 is 60. So you can see those 3 6-degree angles. And what I've done with the lengths of the 3 sides, we know they're congruent, I've let them be a length of 2 units, just to make everything simplify nicely. So as I do that, I want to look at forming a right triangle. So to do that, we drop the perpendicular from the top of this triangle down to the base. And of course, dropping that perpendicular as it intersects the base, it intersects at a 90-degree angle. So you can see we're forming two right triangles within this equilateral. Now, as we drop the perpendicular in an equilateral triangle, right, we end up forming two 30-degree angles because it bisects, right? This perpendicular bisects that angle. So with that said, we've got a 30-degree angle up here. We can write in those two 30-degree angles. So these are a 30, 60, 90 right triangle. So that allows us to now evaluate, right, our different trig function values, right, using these acute angles, right? So we can find the sine of 30 once we find the opposite side's length and the hypotenuse, which is 2, you can see. But let's go back to the three sides. What are their lengths in these right triangles that we've formed? So as you look down here at the base, one thing we know from geometry is that the base has been bisected. So we know if our length of the base was 2 units, we know now this perpendicular has bisected it, split it in half here. So these would each be length of 1 unit, right? It bisects that base into half. So we see now, again, this leg here, and this whatever right triangle you're looking at, right or left, is base of 1 unit, right, on the right triangle base. And then our height, now we need to find the height. So to construct this, let's go ahead and find the height of this, x. So to find x, right, we can go ahead and use the Pythagorean theorem. So let's use the Pythagorean theorem, and let's go find our missing side's length. So we know, again, the square of the hypotenuse. So remember, Pythagorean theorem, hypotenuse squared equal leg squared plus leg squared. Right, the sum of the squares of the two legs. So as we plug in that information, we've got 2 squared, the hypotenuse 2 units in length. One of our legs is 1 unit, 1 squared, plus the other leg, which we're trying to find its length, is x. We assigned this variable, it's unknown. So with that, we have 2 squared, which is 4, equal to 1 squared, which is 1. As we solve that for x, well, we go ahead and subtract 1 on both sides. X squared is equal to 3. And then we can take the square root of both sides to get x. We don't need to worry about a negative, right? We're dealing with lengths. Even though it's an even root, be positive or negative. But we end up with the square root of 3. So we found x now. So this side here, there's a square root of 3 units in length. Well, now we're good to go. So now let's use our right triangle trig, right? Let's use our right triangle trig, and let's go ahead and evaluate our 6 trig function values for 30 and 60 degrees. All right, so starting with, for example, let's go with 30 degrees. What would be the sine of 30 degrees? Sine is opposite, right, over hypotenuse. So that will be 1 over 2. So the sine of 30 degrees holds a function value of 1/2. All right, so there's the sine of 30. Now we also know from that cosecant function value. And I'm going to go ahead and write cosecant since it's the reciprocal of sine. And of course cosecant's hypotenuse over opposite. So it would be 2 over 1, which is 2. So it's cosecant, it's a reciprocal function. And let's go ahead and look at cosine. What would the cosine of 30 degrees be? Well, it would be the adjacent side's length to 30-degree angle over your hypotenuse. So looking at your 30-degree angle, the adjacent side is the side x there, the square root of 3 units in length, over the hypotenuse, which is 2 units in length. So square root of 3 over 2 is cosine of 30 degrees. And then as we look at its reciprocal function, which reciprocal cosine is secant, secant of 30 degrees, which is defined as hypotenuse over adjacent, is equal to 2 over the square root of 3. Now that we don't like because we need to rationalize that square root in the denominator. And as we do that, we end up with 2 square roots of 3 over 3. So there's the secant of 30 degrees. And then to finish it off, let's go to tangent. We know the tangent, 30 degrees. Definition, tangent in a right triangle is the ratio of opposite side to adjacent side's length. Opposite side is 1 unit, adjacent side is square root of 3 units. 1 over the square root of 3, and again, we want to rationalize. So let's go ahead and multiply numerator and denominator by the square root of 3 so we can create that square. And we end up getting the square root of 3 over 3. So there's the tangent of 30 degrees. And then to finish it off, let's go to cotangent. So cotangent of 30 degrees equal to adjacent side's length over the opposite side's length, which would be what? Adjacent side length of 30 degrees is square root of 3. Opposite side's length is 1. Square root of 3. There's our value for cotangent. So cotan of 30 degrees. All right, now that's 30 degrees. So again, we want to have these memorized, but if we don't, right now we're getting familiar with them. You can always prove them using right triangles, right? Using these equilateral or isosceles triangles, right, that we've proven here in our last 2 slides. So it gives you a visual, shows you where it comes from, using our definition of right triangle trig. Now again, that's with 30 degrees. Of course, we could go ahead and do, for example, let's go ahead and look at 60. So how about our 6-degree angle measurements? What would the sine of 60 degrees equal? What's the opposite over the hypotenuse? Well, the opposite of 6 degrees is square root of 3, and the hypotenuse is 2. Right? The sine of 60 is the square root of 3 over 2. Which you remember is the value of the cosine of 30. I mentioned briefly earlier in our lecture that cosine and sine are what we call cofunctions, sine and cosine. And when we have complementary angles, like we do with 30 and 60, they sum to 90, their function values with cofunctions are always the same. And that's a theorem we're going to mention in a little bit. That's the sine of 60. And of course, if you wanted to go to the reciprocal functions, right, you say, well, what about the cosecant of 60? Cosecant of 60 would be hypotenuse over opposite, which would be 2 over the square root of 3, which is we rationalize. We'll go ahead and rationalize that. Square root of 3 multiply numerator denominator. As we do that, we get 2 square roots of 3 over 3. There's cosecant of 60. All right, and then let's go to cosine. As we look at all 6 of them, cosine of 6 degrees, we know definition, adjacent over hypotenuse. So that will be 1 over 2. Cosine of 60 is 1/2, just like the sine of 30 is 1/2. Cofunctions, same function value. And if you look at the reciprocal, of course, the reciprocal function, that implies secant. Secant of 60 would be the reciprocal of that, would be the hypotenuse over the adjacent side, which would be 2 over 1, or 2, right, would be that with 60. And then to finish it, right, the only one we haven't done is tangent. So let's go look at the tangent of 60, which is opposite over adjacent, which would be square root of 3 over 1, which is the square root of 3. And if you remember, that is what we had with the cotangent of 30. It's cofunction with the complementary angle. And then looking at the reciprocal function, what is the cotangent of 6 degrees? What's adjacent over opposite? Adjacent over opposite is 1 over the square root of 3, which is, we rationalize that, that's square root of 3 over 3. Which again is the exact right value we had earlier, right, as we looked at tangent of 30. It's cofunction with the complementary angle. So square root of 3 over 3. But there they are. So there are 30 and 60 degree angles. So we talked about 30, 45, 60. We want to know those. We want to have them memorized. We're going to refer to them as we move on through the semester. We're going to always see these come up in our problems. We want to know them to make our work a little easier and a little simpler. One thing I do want to make note of, if you want to, pull up your calculator. All right, so I'll pull up my TI-84 version here. In your TI, if you want to look at different trig function values with your calculator, right now we're dealing with angle measurements. You do need to hit your mode key. So hit the mode key on your TI, and you see in the mode, if you go down to the third row there, it says radians or degrees. So right now I'm in radian mode. That's the default mode. So you will probably have to hit the enter button and turn on degrees. And then hit second button and quit. Second mode, of course, is quit. And you could type in, for example, we know the sine of 30 degrees is 1/2. So if I type in the sine of 30, it knows 30 is degrees, not radians. Radian measure is something we'll talk about later in this chapter. But right now we're in degrees, so we'll make sure it knows that's one of those acute angles from our right triangle. And if you hit that, we're going to get 1/2. Of course, it says, 0.5, which we know is 1/2. Put in decimal form. Now, if you wanted to look at, for example, how about the sine of 60 degrees? Now, the sine of 60 degrees, as we looked at earlier, is an irrational number. It's the square root of 3 over 2. Now, it's not going to write square root of 3 over 2 on your calculator. It's an irrational number, square root of 3 divided by 2. Right? It's rounded decimal, 0.86602544038. That's an approximation. We want square root of 3 over 2. Now, you can match that up. You say, well, how do I know it's square root of 3 over 2? Let's type in square root of 3 over 2. And we'll make sure that it matches up, right, with that. And you see that is 0.866. Just like the cosine of 45 degrees, we know it's square root of 2 over 2, which square root of 2 over 2 is 0.707 approximated. But again, we're not looking at decimals. We're not needing to round anything because we know how to find the exact, right? We can prove it with right triangle trig, with our isosceles right triangle, or with our equilateral triangle, right? We can introduce the 30 and 60 degree angles. So with that said, you can see those function values and those trig values with our calculator. Now, you say, well, how about, I see sine, cosine, of course, tangent. If you want to do example, tangent 45 is 1, which we proved earlier. It's a ratio of the two legs of your isosceles right triangle, opposite adjacent. It's about 1 unit. But with that said, how do you put in cotangent, or how do you put in cosecant or secant? All right, you don't need any programs. You can use your sine and cosine and tangent keys. So, for example, if I wanted to look at the cotangent of 45, right, or the cosecant of 60 degrees, all right, all you got to do is use your reciprocal properties. So, for example, if I wanted the cosecant of 6 degrees, I could type it in as 1 divided by the sine of 60 degrees. All right, and it gives me 1.547005384. It gives me an irrational number, right, with cosecant of 60. And, of course, we looked at that earlier. Go back to our notes, right? We just looked at the cosecant of 60. All right, cosecant of 60 is 2 over square root of 3, or 2 square root of 3 over 3. You see here in our notes. So, again, if you wanted to, type in 2 divided by the square root of 3. What's 2 divided by the square root of 3? Let's put that in here on our calculator. There it is. 1.15470. Again, irrational number, but we want the exact. We do not need to round it. Most likely, they're going to ask you in your work and your problems and your practice and your homework, they're going to ask for the exact when they're dealing with special angles. They're not going to ask for a decimal. So you need to be able to refer to those function values, be able to prove them if you need to. Right now, you can derive them from your triangles. But you want to know these values and have them memorized. We're going to keep working with them and make the process a lot easier later on as we get into different problems. So I want to show you that, just some trig function values. I put in our notes, of course, a summary of all of them together. I'll give you a table of your values so you can see them here, and you can see the similarities too with those cofunction properties. Again, remember the complementary angles, they hold the same value. So 30 and 60, you can see everything switches up. Sine of 30 is 1/2, cosine of 60 is 1/2, for example. Cosine of 30 square root of 2, just like the sine of 60 square root of 2. So you see that in there. Now, down here below, you can see where they derived from with our two right triangles. One of them derived from the equilateral and the other from the isosceles. Going to the similarities, here's the complementary angle theorem for cofunctions. So sine of theta will always equal the cosine of 90 minus theta, right? How do you find the complement? Complementary angles are two angles whose sum is 90. So 90 minus that angle. So just like sine of 30 is equal to cosine of 60. Just like the sine of 45 is equal to cosine of 45. They're complementary. They're both equal to square root of 2. Right? So again, you can see that's true with all cofunctions. Cosine and sine, tangent and cotangent, secant and cosecant, cotangent and tangent. Those are cofunctions. So that's a nice theorem to help you remember those function values. If you know one, you'll know the other. So again, that'll help you with 30 and 60, remembering those. So let's get more practice with that. It says find the exact value. So we don't need a calculator. So find the exact value for these expressions. Now these are our angles we just finished working with. Cosine of 45 degrees. Well, cosine of 45 degrees, we should know, is the square root of 2 over 2. So we'll go ahead and plug that in here right beneath it. Times the cotangent of 45 degrees, which is 1. Right? Cotangent and tangent, 45, both 1. Sine of 45 and cosine of 45, both square root of 2 over 2. So in the end, we get our function value. We get square root of 2 over 2. Again, we can evaluate easily without a calculator involved. Cosecant of 45 degrees. Well, cosecant of 45 degrees is equal to the square root of 2. If you want to go back, refer to those values in your table, you can, but you should know those. That's square root of 2. And then I've got the tangent of 45, which is 1. The square root of 2 times 1 is square root of 2. Sine of 60 times the cosine of 45 degrees. All right, let's go ahead and evaluate. Now remember, we mentioned earlier the cosine of 30 was square root of 3 over 2. So sine of 60 is going to be the same function value. It's going to be square root of 3 over 2. Cosine of 45 is square root of 2 over 2. As we simplify, of course, multiply the numerator. Square root of 3 times square root of 2 is square root of 6. 2 times 2 is 4. So we do the product. So we end up with square root of 6/4 in our value. Tangent of 30 degrees. Tangent of 30 degrees is square root of 3 divided by 3. Square root of 3 over 3. Plus cosine of 45, which is square root of 2 over 2. Now on this, we can't add until we have a common denominator. So our LCD, our least common denominator, is 6. So let's go ahead and rewrite both of these with a common denominator. So I'll multiply both numerator and denominator by 2. This one by 3. As we do that, we get, what, 2 square roots of 3 over 6 plus 3 square roots of 2 over 6. As we add those together, we end up with 2 square roots of 3 plus 3 square roots of 2 divided by 6. So we sum those two together. So there's our value, right, our exact. You can put it in your calculator if you wanted to check it. Right, we didn't need a calculator to get it, but that's the exact, and you could type that in, tangent of 30 plus cosine of 45, right, and you can look at it and get the decimal on your calculator. It'll match up with that fraction. All right, how about tan squared of 45 degrees? Well, 45 and 30, so tangent of 45 is 1. So that's 1 squared. Sine of 30 is 1/2. That's 1/2 squared. So this is 1 plus 1/4. Which 1 plus 1/4 is what? 1 1/4 of 5/4. And if you wanted to, we could go ahead and rewrite this with a common denominator. That's the same thing as saying 4 over 4. So again, 4 over 4 plus 1/4 is equal to 5/4. function value. All right, moving on, let's go to DMS notation. Degrees, minutes, seconds. DMS notation, well, you see this a lot in navigation, mapping. Give a location by degrees, minutes, and seconds. What it does, give us a more precise location of our measurement of angle. With that said, when we have a decimal degree, we can convert that decimal over to minutes and to seconds. What we got to remember is the conversion factors. So remember that 60 minutes make a degree, and 60 seconds make a minute. If you remember that, you can easily convert back and forth between the two, from decimal to minutes seconds back to decimal. So again, what do we mean by DMS notation? 62 degrees, 10 minutes, 48 seconds. That's 62 degrees. We use degree symbol, of course, for degrees. We use the minute notation, which is your prime or single quote notation. And this is actually on your calculator, and I can show you that on your TI too. And then you have your seconds notation, 48 seconds on there. With that said, you don't have to have a calculator do your work for you. You can do the conversions by hand. And just want to show you how to do that. So let's take a look at an example. Let's go ahead and look at this first one. So we got 62 degrees, 10 minutes, 48 seconds. It says it's equal to 62.18 degrees. So where did that come from? So how do we convert that by hand? We were doing that by hand. Well, we would start off with first 48 seconds. Let's convert that to minutes. So if we want to convert that to minutes, we would take 48 and divide by 60, because we know there's 60 seconds in a minute. So we would go ahead and find out what 48 divided by 60 equals. All right, and we can reduce that if we wanted to. We know that 12 divides into both. 12 times 4 is 48. 12 times 5 is 60. It's 4/5, which is 0.8 as a decimal. So right now, if you're looking at that, right, that implies we have 62 degrees and 10.8 minutes. So I've taken my seconds and converted over to minutes. It gives me 0.8 as I reduce it. Now, how about converting that over to degrees? So now we say, well, how many minutes in degrees? So we can take 10.8, right? We can divide by 60. So we'll get our number. So what's 10.8 divided by 60? So if you want, we can go to our calculator. Let's pull it back up. What's 10.8 divided by 60? It's 0.18. So 0.18. So you go back to your problem. Yeah, that's equal to 0.18. So that's what? 62.18 degrees. There's your conversion. Right. So again, let's take in DMS and get back into decimal. How about we go the other way? How about we're given the decimal and we want to go back to degrees, minutes, and seconds. And sometimes we'll need to round the nearest second. You might have a decimal in your second notation, so we'll round it. So for example, we want to convert this over. So 0.14 degrees. Well, we know there's 60 minutes in a degree. So the first thing we'll do is take 0.14 and times it by 60. So 0, 6 times 4 is 24. 6 times 1 is 6 plus 2, we carry is 8. Got 2 decimal places. I got 8.4 minutes. So again, there's our conversion. So this is equal to 20 degrees and 8.4 minutes. Well, now let's convert the minutes over. So we know there's 60 seconds in a minute. So let's convert to seconds. So what's 0.4 times 60? 0. 6 times 4 is 24. We have 1 decimal place. There it is. There's our conversion. So in the end, we have what? 20 degrees. And we have 8 minutes and 24 seconds. There it is, 20 degrees, 8 minutes, and 24 seconds. So converting that over. So you can see that conversion there as we're looking at these problems. Remember your conversion factor. 60 minutes make a degree, 60 seconds make a minute. So you can do the same thing with examples B and C. And you also have on your calculator, I'll show you on your TI. Let's pull up your calculator here. On your TI, if you look at the calculator here, you go to your angle menu.